Okay, so basically in this video we will talk a little bit about the resonant frequency and basically how you can calculate that. So let's say that you have a circuit, for example some circuit like this. You have some inductor over here, and then you have a capacitor over here, and then you have a resistor over here, and this is basically your V of out, and this goes to ground. This becomes your V of in. Of course, I think I'm going to do a quick demonstration of this circuit on an oscilloscope as well, to see basically what, just put together a quickly a circuit using some capacitor and some inductor and a resistor, and see what we get over here. Okay, so what I'm going, so now the circuit that you have over here, your V of out is actually your V of R, is the voltage across this resistor over here, and there will be some sort of reactance over here for related to the inductor. There will be some reactance related to the capacitor, and at some point you are going to have some peak in your voltage, meaning that at some point in frequency, let's say this is F of in and this is V of out, at some point over here you are going to have although this is I don't know if it's a low pass filter or high pass filter. Let me see. If you have a low frequency, you will have low and high reactances across these two, right? And then so they kind of cancel each other out, but there is no way to know that, but that depends on the values of these two. So there is no way to tell whether this is a low pass filter or high pass filter. It mostly depends on the values of your capacitor and inductor that you choose here. But basically, whether it's a low pass filter or high pass filter, we will see about that. Okay, but basically you are going to have some sort of peak over here, where basically your voltage gets to this point and then goes back down. Okay, and this peak is going to happen at some frequency which is called F of R, which is basically the resonant frequency. The resonant frequency. And how that happens is actually interesting, meaning that you need to find the frequency for which basically you need to find the frequency for which the net reactance of these two components is going to be equal to 0, meaning that you have some reactance over here related to your inductor, which is basically X of L, and you have some reactance over here which is related to your capacitor X of C, and these two are actually dynamically kind of working together depending on the frequency too, and you will have some voltage drops across these two components here, and then as a result of that there is some voltage drop across this resistor, which is your output. Okay, now what happens is that at some point the the reactance of this of the inductor and capacitor, they kind of cancel each other out. And well, if that's the case, then you have basically no net reactance in the circuit, meaning that the net reactance in the circuit is zero, meaning that there is no voltage drop across these two components. I mean, practically there is, of course, in reality there is voltage drop across these two components, but it's actually happening so fast that then the net result of that looks like, and they are basically, with that speed, they are canceling each other out. That's then you will practically get that voltage across your output. Okay, so in case I confused you, I usually do that. I usually confuse people. I don't really intend to do so, but sometimes you have to confuse people. Well, you know, I repeat this, there is some sort of frequency which is called the resonant frequency, and at that resonant frequency, your net reactance in the circuit is going to be equal to zero, meaning that these two reactances are going to cancel each other out, meaning that your X in the circuit is going to be zero. And what that means is that and you know that X is equal to X of L minus X of C. So if you find that frequency where X of L minus X of L minus X of C is equal to zero, that frequency is called the resonant frequency. So if X of L minus X of C is equal to zero, what that means is that your X of L is equal to X of C. And using this equation, you can simply use and basically find the frequency, because you know your X of L is equal to 2 pi FL and X of C is equal to 1 over 2 pi FC. So if you cross multiply, what you will get is, or if you divide both sides of this equation by 2 pi FC, you'll get 2 pi FL over 2 pi FC. I'm sorry, if you multiply both sides of this equation by 2 pi FC, I want to get rid of this thing over here. So I multiplied 2 pi FL and multiplied by 2 pi FC, which is the same thing as cross multiplication anyway, is equal to 1. So this is equal to basically 4. This is equal to 2 times 2 is equal to 4. Pi times pi is equal to pi squared, and this is F squared LC is equal to 1. And then your frequency is going to be equal to F squared is equal to 1 over 4 pi squared LC. And then basically F is going to be the square root of 1 over 4 pi squared LC. And then if you can take this part out, so you can write this as the square root of 1 over 4 pi squared times basically 1 over LC, and then you can write this as the square root of 1 over 4 pi squared and times the square root of 1 over LC. And you know that the square root of 1 is equal to 1, so you can simply write that 1 over the square root of 4 pi squared, which is equal to 2 pi. And again, the square root of 1 is equal to 1, so that's 1 over square root of LC. So what that means is that that basically F is equal to 1 over 2 pi square root of LC. 1 over 2 pi square root of LC. That's how you can calculate the resonant frequency. and that's basically called f of r. So in short, basically f of r is equal to 1 over 2 pi the square root of LC over here. Now when this happens, you get your peak voltage over here, because there is practically no voltage drop across these two components, and all of your voltage is going to appear across this resistor. But again I repeated that. I should repeat that. Basically, it's not possible that there is no voltage drop across the inductor and the capacitor, because they are in the circuit and they are actually doing something at that frequency, and they are, if you take a look at the oscilloscope and how the sine waves are actually working together, they're kind of at any moment they're kind of working and also canceling each other out. So then the net result becomes basically most of your voltage, about 90-95% of your voltage appearing at your output. So that's basically what this whole thing is about. So that's the whole concept of resonant frequency. Now, in order to, let's do a couple of examples using this in order to understand this better. And I think I'm going to put together a quick circuit to show you basically where this peak is actually appearing. And it would also be helpful if you had using a well, you would need some more more advanced test equipment than I currently have in order to see basically to be able to actually generate this graph on a piece of test equipment, something like an oscilloscope that basically has a screen. So there is something called I think you can do this with a test equipment called it's actually called a spectrum analyzer. Okay, so what this thing does is that, you know that on a basically regular oscilloscope, you have basically these two axes over here. If this is an oscilloscope, so what happens is that you have a horizontal axis over here, which is time, and you have this vertical axis over here, which is voltage. So you always have, for example, something like this, and this is basically at any point the oscilloscope is telling you where the voltage is with respect to time. For example, at this time t1, this is your voltage over here, V1, for example. At this point, for example, at t2, this is your signal over here. At this time, for example, t3, for example, this is the level of your signal, and so on and so forth. So basically, an oscilloscope is giving you basically it shows you voltage over time, right? Now in a spectrum analyzer, you are actually you are able to see frequency. You have f over here versus, I think, versus voltage or power or something like that. You can also change it and so on and so forth. But I'm pretty sure that using a spectrum analyzer, you can actually create this graph live on a spectrum analyzer. But it doesn't really matter. We could actually take a look at the circuit and pick a few points and then draw a graph of basically what's happening in the circuit. But before I go any further, I need to basically put together a few components to put a circuit together, and then we will do also a couple of examples on this concept in order to understand the resonant frequency better. I'll be back in just a few moments. Okay, so now in order to see how this circuit works, I'm just going to put together some simple inductor. The values are not that important right now, because I don't want to note down any values, and I just want to see the peak. And I have this inductor connected to this resistor, and then I just I connect to this. I just connect one end of this capacitor to this inductor, meaning that first the inductor, then the capacitor. When I have to, so let's put the capacitor first. It doesn't really matter right now which one is first, which one is last, because I'd have to unsolder this thing from here, which is right now not that important. So I connect this capacitor over here, and that's basically that. Okay, so now my input becomes this capacitor, and then that goes into this inductor, and this resistor goes to ground. Okay, and my output becomes where the basically inductor is connected to the basically my output is going to be something like this. So right now the circuit that I have is basically I have some capacitor over here. It's connected to an inductor, and then that inductor is going to a resistor, and that's connected to ground, and that is basically my V of out, and that is my basically V of in. So this is the capacitor, this is the inductor, and right here is the resistor that goes to ground. So now I just give this circuit some give this circuit some okay, so this is the signal generator that comes in. So this is the ground I connected to the resistor, and this is my input I connected to the capacitor. Okay, and you have to excuse these. They have made these clips in such a way that they don't hold on. I think they have done that intentionally. Otherwise, there is no reason why they don't hold on so many times, you know. Okay, so I connect my oscilloscope here. I connect the oscilloscope channel 1 to input. So this is channel 1 I connected to the input, and the other one goes to ground, and channel 2 to the output, which is basically this point where the inductor is connected to the resistor. So that's basically my ground. That's what I'm talking about. Okay, and this goes to ground as well. So this is basically my circuit right here. Put it right here and hope that they don't get disconnected again. And if I of course you're not seeing anything here. So right now I'm getting the signal from this signal generator. It's right now at about 8 hertz or so, and I'm reading the output, the signal over here, the frequency. It's showing 16 kilohertz or so, which is garbage value. For now, we don't read on this until we get to higher frequencies. And on the oscilloscope, let's see what my peak-to-peak voltage is. So this is my output. This is my output. I don't know why I cannot see anything. Okay. So this is my, okay, this upper wave over here, this is my input. Okay. This is my input, and this wave down here is my output. And it seems that the output is right now on, I've set this to 20 millivolts, and this is on 2 volts. So that's basically how many times 20 millivolts would be basically times basically 10 would be 200 millivolts times 100 times smaller. The output is 100 times smaller here. And the frequency, as you can see, it's very low. It's about nothing, about 10 hertz or so. So now if and the peak-to-peak voltage seems to be, I don't know why it's at 5 volts or so. It's not supposed to. Okay, it's because of the frequency. Because of the frequency, I've set my output by input voltage to maximum, which is about probably around, I think, about 20 volts, 25 volts or so on the generator. But because the frequency is so low, that the peak-to-peak voltage comes basically reduces as well. So now I want to get this to some frequency where we can actually see something, and we have some voltage here. So as you can see, my input voltage is at about 2.4 times 10 is equal to 24 volts peak to peak. Okay, my output voltage is about nothing. Is actually about 10 millivolts or so. So this is 2, so that's about 40 millivolts or so. So the output right now is actually very, very low. Now if I increase the frequency here, go back here and multiply the frequency by a factor of 10. So right now I'm at about 800 hertz or so. Or let me see. No, sorry. I'm at about what is it? 10 times 30 hertz or so. Okay. So my output, you see the output is actually increasing, and my input is at about 1, 2, 3 divisions times 10 is 30 volts peak to peak. My output is at about 60 millivolts peak to peak. So if I increase the frequency here, go all the way up to 50, 60 hertz or so, you see that my output is increasing. Right. So now my output is at 2.4, 2.5 times 50 is equal to 125 millivolts or so. And the output is still at about 30 volts peak to peak. And I increased the frequency a little bit more to about 10 times 100 hertz or so. and this is my output at 250 millivolts peak to peak. Okay, so let me bring this down a little bit, and then go back to 10 hertz, and then multiply by 10, so that's again 100 hertz, and then increase the frequency a little bit. You see, as I increase the frequency, the output is actually getting bigger and bigger. So increase the frequency again, the output is getting bigger and bigger. Increase the frequency a little bit more, and still the output is growing. And now we can actually see we have it's about 1.5 volts peak to peak. So if I go down 1 and I go back to the beginning of the range, multiply by 10, and the same, now I have the same frequency, and I start increasing the frequency again, and you see the output is growing again, increasing. Right now I'm at about 2 kilohertz frequency. Okay, so 2 kilohertz, you see that the output is still getting larger and larger. Right now at about 4 kilohertz peak to peak, 4 kilohertz frequency. So, and now the output is at about 10 volts peak to peak. I still have to go a little bit, and I could still keep going. Make this a little bit smaller here. So this is at 7 kilohertz frequency, 8 kilohertz, 9, 10 kilohertz, and now my output is at about 3.2, about 15 volts peak to peak. Okay, make this a little bit smaller here, and go to the beginning of the range again, and multiply by 10, and now the frequency is still the same, 10 kilohertz, and then I start increasing the frequency. As you can see, my output is getting larger and larger. Now I'm at about something about the input, so it's basically 2.6. That's 26 volts peak to peak. My input is at 2.8, and I think here the output is not going to get any bigger. Okay, so you see now I'm increasing the frequency, and the input is somewhere about the output, so you have 2.6, 2.7, and this is 2.67. the same, I have the same output right now as the input. And now I go to the beginning of the range and multiply by 10, so I have the same frequency again, and I start, and as you can see right now I'm at about 105 kilohertz, and my input and output are actually the same right now. But as you can see, if I increase the frequency now, there is going to be no change in the amplitude. The amplitude is remaining the same, actually getting a little bit higher than actually the input probably, and that's because of the inductor. Sometimes your output goes higher than your input, and that happens when you have an inductor in your circuit. And you go all the way up to here, it's still increasing, and now I'm at about 700 kilohertz. Okay, so you see that now my output is actually bigger than my input. My output, this is my input, this is my output, they have the same scales. My output is bigger than the input, so I keep increasing. I'm about 700 kilohertz, and right now I'm at about 1 megahertz. So I go to the beginning of the range and then multiply by 10, so I'm still at 1 megahertz. And if I increase the frequency now, you see that now that is that spot where the output starts going down. You see what happens over here. Right now I'm at about 1 megahertz. I'm at about 1 megahertz, and if I keep increasing, go to somewhere about 1.2 megahertz, the output starts going down. Okay, so right now my input outputs, you see the output is actually larger than the input. Okay, but if I increase the frequency, you see the output starts going down from here. So it's about 1.148 megahertz. If you want to see the frequency here, you can actually read it here. So it's about, because sometimes you cannot really trust this. I mean, for ballpark values and things like that, you can trust it. Otherwise, if you want to have a better reading, you need to do it manually. So I'm at 0.2 microseconds, so 1.1234, 4.25. So I'm at about 4.25, 4.25 horizontal units times 0.2 microseconds. That's equal to 8.5 into 10 raised to the power negative 7 seconds. And then if I take the reciprocal of that, my frequency is 1.176, and this counter tells me 1.148. So I take this frequency as that peak, as that resonant frequency, and we can even do some calculations using this circuit. So let me bring the camera down here, and then now we will do some calculations using these values. So let me actually get rid of this circuit. Okay. Okay, so what you saw was that basically the circuit that I had was this circuit. The capacitor was 0.01 microfarad. The inductor was 110 microhenry, and the resistor was 990 ohm, and the frequency where the output was at the peak was 1.176 milli, not milli, 1.176 megahertz. So the frequency was 1.176 megahertz. Okay, so I don't really know if I'm going to need the voltage, but hopefully not, because I didn't actually do any reading of the voltage. Most probably we're not going to use to need them. Okay, so at this, if you calculate if you calculate the reactance of this capacitor at this frequency, and also the reactance of this inductor at this frequency, let's see what happens. So X of L is equal to 2 pi FL, which is equal to 2 pi times frequency times 1.176 into 10 raised to the power 6 hertz that's 1.176 megahertz, times the L, which is 110 microhenry, so times 10 raised to power negative 6 Henry. So these two you can cancel out, and then you have 2 pi times, let me calculate it, 2 pi times 1.176 times 110 is equal to 6468 by 25. 6468 divided by 25 pi, which is roughly 812.8 ohm. That's in ohm, so 812.8 ohm. Okay, now x of c here is equal to 1 over 2 pi fc, which is equal to 1 over 2 pi. F is 1.176 into 10 raised to power 6 megahertz, and times the C with the capacitor was 0.01 microfarad times 10 raised to power negative 6 farad. These two you can cancel out, and then you have 2 pi. You have 2 pi times 1.176 times 0.01 is this value. Take the reciprocal of that. It's 13.533. 13.5 is equal to 13.533, or I'll take it as 13.5 ohm basically. Okay, so now there is something wrong here, because at this frequency, if our assumptions are right, actually the voltage for this circuit, as I was looking at the output, the voltage was kind of, I mean, the graph, if I were to do a graph of what happened there, was that basically if this was f of in, now I don't know at what frequencies they actually happened, the voltage was kind of something like this, meaning that the output was constant for a while, and then it got to a peak, and then it came down, and then started to come down to decrease like this. It was kind of like this. So we had also this basically this distance over here where the output was actually kind of constant, then it got to a peak, and then after that basically started decreasing. So I'm not really sure if this frequency is actually 1.176 megahertz is actually the resonant frequency of this circuit. And we could actually calculate this, meaning that we said that f of r is equal to 1 over, if I'm not wrong, 1 over 2 pi square root of LC. Okay, so this is for this particular circuit, it's actually equal to 1 over 2 pi the square root of L, which was in this case 110 microhenry into 10 raised to power negative 6 Henry, times the capacitor, which was 0.01 into 10 microfarad, so into 10 raised to power negative 6 farad. Okay, so if I calculate this thing, I have 2 pi times the square root of 110 times 0.01 into 10 raised to power negative 12. That's equal to this value, and then if I take the reciprocal of that, I'll get 151,748, and that's the frequency where that's the frequency. This is 151,748 Hertz. Okay, that is f of r. That's actually the frequency where the output actually got stable over here, and then it was stable and steady and constant for a while, and then it got to a peak. Okay, so this peak is actually in this case is the meaning of that is actually something else. It's not that peak which is related to the resonant frequency. Okay, so now if I use this frequency for this circuit, most probably, certainly the x of c and x of l are going to have the same values, because we got this formula, but by equating these two formulas together, and then we got this formula here. Okay, so now let me actually connect this circuit one more time to the signal generator and see what we see, and I will actually drive the signal generator to this frequency. So this is the circuit. It's not that hard to connect it again. So this is my circuit. This is my input, and this is the output. And then all I need to do is just connect this to the input. And connect this to the output, to the ground. And this is my output actually. Okay, so and this is the ground. And right now, as you can see, if I go somewhere near the resonant frequency for this circuit, as you see what happens. So right now I'm at about 1.1 megahertz. I want to go down to basically around 150 kilohertz. So I go to 100k, and 15 times 100k is actually, that thing is not possible. So let me see. So if I go to, that's 2. If I go down here and go, that's going to be 1 megahertz, 150 kilohertz. So that's going to be around 1.5. So I start somewhere over here, so 10k somewhere over here. Okay, so I go, now this is around 100 kilohertz or so. So I slow down the oscilloscope, and you can see that actually at this frequency, my input output are actually kind of the same. This is 3.7, so something like 3.7, and this is 1, 2, 3, 1, 2, actually 2.7 and 2.7 are actually kind of the same. So if I have to go down a little bit, so they are actually still the same, kind of. Okay, so not the same still. Okay, so it's now increasing, and I'm at 59, around 59, 60 kilohertz, and it's still increasing. Now they are the same. Okay, as you can see over here, they are exactly the same. And if I go down to the beginning of the range, and multiply by 10 and start increasing the frequency, you see right here I'm constantly increasing the frequency and not much is actually happening. You see? So it goes all the way up to 600 and 800 and so on and so forth. Go to the beginning of the range, and here it starts diminishing. So it kind of starts around 500 kilohertz or so. So it's kind of starts around 500 kilohertz or so, or even less than that. Still the same thing. Okay. Okay, so now at 10 kilohertz, my output is of course is considerably, is around half my input. So you see over here, now my output is about somewhere near my output, and then what happens is that at 61, right now I'm at 61 kilohertz. Okay, right now I'm at 61 kilohertz. Let me show you the counter as well so you can see what's going on. And not much is happening here. Okay, that's basically where you go to the, that's basically where you get to the peak. Okay. That's where you get to the peak, and then okay, so that's where it gets smaller and smaller. Okay, so that's basically around 1.4 megahertz. You see what happens at about 1.3, 1.4 megahertz. It's going down. So now the maximum amount of output, if I were to basically look for the maximum amount of output except for the peak, let me put this camera on this stand. Okay, so now if we were looking for the maximum amount of voltage or output except for that peak, let's go down to about we need to go down much lower here. So about, this is about 283. You cannot see anything here, and you see the output is very low here. I have kind of the full output, the full input, and if I increase my frequency here, you see not much is happening here. Okay, so now it's frequency times 10. Now my output is over here. Frequency times 10. My output is, oh sorry, divided by 10. Sorry. So frequency times 10 right now I'm at about, so I have to go back here. So right now I'm at about 9-10 kilohertz or so. So 10 kilohertz. So if I go 20 kilohertz and right now I'm going, I have around 45 kilohertz or so, and my output is at my output is at 2.6, and this is at 2.8 or so. So I increase the frequency a little bit, and you see on this range, it's actually kind of constant, not changing. So right now I have the same output, I have the same voltage for output as for the input. And it happened actually a long time ago. Okay, so you see over here, it happened at this frequency, about 66 kilohertz or so. And then from here, if I increase my frequency, what happens is that if I increase my frequency, not much is happening. And if I go down in range and then multiply by 10, still not much is happening. And over here at about 175, and right now I'm about 135, 147, right? And at this frequency, which is very close to the resonant frequency that we calculated, the input output are kind of the same. And right here, if I increase the frequency, you see what happens is that the output starts basically going higher a little bit, but you have to drive it all the way up to 340 or so kilohertz, and still not much is happening, and still increasing, and still increasing. Okay, going down in range and then multiply by 10. And right now I'm at about 1.27 megahertz, and over here, right over here, the output starts decreasing at about 1.2 megahertz. So the circuit is but well, the output of this circuit is, you see, if I go all the way up to 10k, 10 times 100k, so if I go all the way up to 40 kilohertz, you see the output is actually the same as, kind of the same as the input. That's 2.8, that's 2.6, for example. And that's kind of the same. At about 80 kilohertz, it's kind of the same. And then above that, it just keeps changing. But now I do not really know how to make sense of this, circuit. But but if I basically go for the resonant frequency, which is 151 kilohertz, it's going to be 151 kilohertz would be somewhere over here. This is 151 kilohertz or so. Okay, and you see that your input and output are exactly the same. So one thing I can tell you, and that is at 140 actually. So that is 1, 2, 3, 4, and 5. So that's 0.2. So that's 1.2, 1.4, 1.6, 1.8. So that's 1.4, 1.5 at 151 kilohertz or so. The output, one thing I can tell you based on what I have seen, is that at 151 kilohertz, which was the resonant frequency of the circuit that we calculated, the output is exactly the same as the input. Well, give or take a few millivolts or so, a few tens of millivolts. It's kind of the same. But we cannot say that the output is the same. The output is the same as the input only at this frequency. There are many other frequencies at which the output has the same value or even higher values than this. So that's basically what we can take from this experiment. Now, I think I'm going to just get rid of this circuit for now and come back over here. Okay. So let me see. Okay, so that was basically a simple experiment that we did. Now, in the next video, for the circuit, in the next video we will do a couple of circuits. Some calculation related to the concept of resonant frequency. So I'll see you in the next video. Thank you.